Oh, hello, everybody. My name is Monica. I am a PhD candidate at the University of Alabama, and I will be talking about unlocking concrete's green potential, integrating supplementary cementitious materials with biomolecule-regulated carbonation. So first, as we all know, the cement industry is one of the contributors of global CO2 emissions. And as part of the Global Cement and Concrete Association, we have a roadmap to achieve net zero by 2050. And this is a goal that's our responsibility as an industry, as society, to get to that goal. It is a very ambitious goal, so my understanding is that just one solution will not suffice for us to get there. So in order to achieve that deep decarbonization, we need to look into multiple aspects. So I'll be focusing on first looking to the compatibility of those methods, whether we can integrate things that are already being used or innovations that are being proposed. Secondly, we need to look into the implementation. If you can look here in the picture, this is the decade to make it happen. So if we have a solution that cannot be implemented right away, that's not going to get us there. And lastly, we want to also consider the performance, because again, you could have very sustainable concrete, but if it's not going to perform and you're not going to be able to design with it, then it's going to defeat its purpose. So we want to make sure that you're not only get to the sustainability goals, but you're also performing very well. So on the one hand, we have supplementary cementitious materials, or SCMs, which are right now the most adopted solution towards the low carbon concrete, because it's very straightforward. You're just replacing part of the cement with those materials. One of the main problems we have with SCMs, though, is problems with low early age strength and delayed setting time. Because of the pozzolanic reaction, it just happens on a secondary base. So you have first the hydration happening, and then later on, the pozzolanic reactivity is going to catch on, and that causes a delay in your performance. So like I said before, we're also focusing on the performance, so we need to address that. And then a second look into SCMs, more recent, we have LC3, which is limestone calcined clay cement, which is a mix of limestone, calcined clays, some gypsum, and clinker. We're able to achieve a lower amount of clinker that way. And besides the pozzolanic reactivity here, we're also able to take advantage of the synergy that we have between alumina and the limestone. So some of the things that you can see with LC3 is the formation and stabilization of more ettringite, which can help with the packing density, as well as the formation of new hydration products like hamite and monocarbonate that have higher bulk modulus, so they can help with the performance as well. And then on the other hand of low carbon concrete, we have the utilization of CO2 in concretes through CO2 sequestration. So mostly we have two popular methods. The first one is carbonation curing, in which you adding the CO2 after you cast your members. I think most of you should be familiar with this. And then some of the main advantages is that you can get improved strength, especially at early ages. So for the performance part, we're happy with it. However, it does have some limited applicability because it requires a chamber. So usually it's used for small members like concrete blocks that have bigger surface and are easier for you to handle. And it could also be applicable for precast, but not for ready mix. So a step further into this would be the alternative of mixing carbonation, in which instead of waiting for you to cast the member and then cure under CO2, you would inject the CO2 directly into the truck or the mixer, so that reactivity could happen during that process. And so now you have more applicability. Now you're open to either precast or ready mix and bigger members. And you do see strength improvement as well, even though it's still not that expressive. And on the negative side, we still have some CO2 being released back into the air, because since it's just being injected directly into the mixer or the truck, you cannot avoid some of it escaping back. And then it defeats the purpose of you're trying to sequester it, but if you're releasing some in the process, it might not be the best way to go. So I'm here to introduce a new pathway that I'm calling the BioCarb method. So the first innovation here is that we're adding the CO2, it's what we call the pre-carbonation. So we're going even earlier on the process, we're using the mixing water together with a portion of the cementitious materials to inject the CO2 and absorb it. So that way you're able to have more applicability and more efficiency on that CO2 sequestration. And so basically the process is broken down into two steps. The first step is when you're producing that slurry that's going to be carbonated. So like I said, you're going to have the mixing water, partial part of your cementitious materials. And then we have the addition of a biomolecule. In this case, we're looking to tannic acid as the facilitator for this process. And then we'll inject the CO2 directly into that slurry. And then the second step, we would add all of the remaining ingredients and make your concrete. And when you look into the process, you can think into applicability right now directly into the plants, because we already have to deal with all that wastewater that's created from the mixing process. So here there's a possibility of using that same water that would have to be treated and disposal as your feedstock, as your carbonated slurry right away. So you would also have a recycling aspect into it. So we need to know, how does it work? So basically with this process, we have nanocalcium carbonate produced directly into that slurry. So you have the advantages of having nanoparticles into a concrete mix, which are filler effect, so you can improve your packing density, as well as the seeing effect. So now those nanoparticles can also help you trigger the hydration process and help you with your performance. So if you look on your left, we have MIP, and you can see the for reference, the two samples with no carbonation. And then if you carbonate with no biomolecule, you do see a shift towards the left for a smaller particle size. And once you add the tannic acid, you can get even smaller particles. Besides that, this is a multifunctional biomolecule. So it can also help regulate the crystal nucleation, orientation, size, and phase of that calcium carbonate being precipitated, as well as help with dispersing the produced nanoparticles, which is another challenge that we see once we have nanoparticles. Usually you will have some agglomeration, but with the biomolecule, you're able to disperse, and that way have a very dense, well-performing matrix. Besides that, that biomolecule will also facilitate the CO2 uptake. So right now, after 60 minutes, we are almost at 8% of the cement weight and CO2 absorption, which is over 30%, over 30 times better than what's being done right now. So you see a much higher CO2 absorption efficiency. And you can also shorten the time because remember, we're trying to make this something that's applicable. So we're trying to shorten that time. So usually 30 to 60 minutes is more than enough for you to have good performance. And then, of course, talking about performance, we also want to look into strength. So again, here I have 3 samples. So basically, we have a control for reference, and then we have the carbonation without the tannic acid versus with tannic acid. And you can see that even though you are able to get some improvement, which would be similar to what you see with the curing and mixing carbonation, because it would be a similar amount of CO2 in the mix. Once you add the tannic acid, you're able to bump that performance to over 25% improvement by 28 days. So for this study, I'm just going to give you a little map so you can follow along. But I'm looking into using Portland cement as the calcium source into the slurry. And then I'm using 3 SCMs to check their compatibility. So we have class F, fly ash, slag, and metakaolin. And where you're looking into 2 main factors here. The first one is the tannic acid concentration, or the tannic acid presence. So no tannic acid versus adding the tannic acid, as well as the carbonation time. So here's just a little diagram for you to follow along. This is how, sorry, how all of the samples are labeled. So you have the T indicating the tannic acid concentration, and then PC indicates that that's the Portland cement that's going into that initial slurry. And then the MC indicates the carbonation time in minutes. So first, we're going to look into the compatibility with the fly ash. So all three samples have 20% of fly ash, and in this case, it's class F fly ash. And we have 25% of the cement into that slurry, so a little bit higher concentration, and we're going up to 90 minutes of carbonation. And you can see again, so for reference, we have the 20% of cement, no carbonation and no tannic acid. And then in green, we have the carbonation without the molecule. And you can see that it actually hurts the strength, mostly because once you have the CO2, you can have some problems with the pH, maybe not trigger the pozzolanic reaction the way you would like to. But once you add the tannic acid, you can see that from 3 days, and it carries on all the way to 28 days, you get improvement to almost 20% at 28 days. And now looking into compatibility with slag. So again, all three samples have 30% of slag present in it, replacing the cement. And then we're following the same scheme. So control, no carbonation and no tannic, followed by carbonation without the molecule. And then the last one, carbonation and the tannic acid present. And again, in this case, you will see a slight improvement without the tannic acid, but once you add the tannic acid, you see that the improvement is even further, getting to 16% at 28 days. And again, no problems with the low early age strength as well. For our last case, we have a compatibility with metakaolin. So in this case, we have 20% of cement replaced. And because metakaolin is more active, we're able to shorten that time. So before we're looking to 90 minutes carbonation, and now there's only 30 minutes carbonation. And we also reduce the amount of cement present into the slurry, so it's a little bit closer to what a wash water would look like. So there's only 10% of the cement in the slurry here. And you can see that starting at 3 days, you're just about the same as the control, and then you reach 15% after 28 days. And then here's another interesting aspect that we notice with the use of tannic acid. So besides the synergy that we have between the alumina and the limestone, like we saw in LC3, tannic acid also shows some synergy with alumina. So through this calorimetry test, we could see that tannic acid is able to promote the C3A reactivity. And this is mostly attributed to the metal polyphenol coordination, which is basically all of those aromatic rings can interact with the alumina present into the mix. And then we thought, well, maybe we can take this a step further since we're seeing some interaction with C3A. And we thought, why not we also adjust the gypsum content? That might help. And surely enough, we're able to improve the performance even further. So you can see that that problem we had at 3 days where you're just above 100%. Now you can bump that strength to 106. And now instead of 15% at 28 days, you're able to achieve 25% at 28 days, which is very good. So to wrap it up, this BioCarb method show good compatibility with all the SCMs here in the study. And then we have the compound environmental impact that we're looking for to achieve those goals. So we have the reutilization of wastewater, which could vary between 5 and 25% of cement present into the slurry, as well as the improved CO2 storage. We're almost at 8% uptake, as well as the improved mechanical performance. We saw 25% increase in strength, and the partial replacement of cement up to 30%. So thank you, and I'm glad to take any questions.